welcome to another AQA AS chemistry video. Today I'm going to be doing a video on redox reactions. Redox reactions are a very important part of chemistry because you need to be able to do half equations. You need to be able to understand what oxidation and reduction is and how to basically understand the mnemonics behind it and understand what an oxidizing agent and a reduction agent, so an oxidizing agent and a reducing agent are. And you need to be able to identify an oxidizing agent and a reducing agent from looking at a reaction and understand which compounds are being oxidized, which compounds are being reduced, and be able to write half equations. So I'm probably not going to go through doing an example of a half equation simply because I haven't planned that for this video. I can probably do it for the next video, but yeah, just going to go briefly what things are, overlay everything. And yeah, so that's it. So redox reactions are important in many areas of life. For example, breathalyzers use redox chemistry, or to understand they use the idea of redox chemistry. And these reactions involve the loss and gain of electrons. So you should understand this topic generally from GCSE, so or what oxidation is and what reduction is. But just kind of remember what it is. Oil rig, remember oil rig. So oil rig is a good mnemonic for remembering the difference between oxidation and reduction. That's oil rig stands for oxidation is loss. Oxidation is loss of electrons, meaning it's oxidation is loss of electrons, and reduction is gain of electrons. So when something is being oxidized, it's losing electrons, and when something's being reduced, we generally describe it as gaining electrons. So when something's being oxidized, it becomes more positively charged because it's losing electrons, and when something is becoming reduced, as it gains electrons, it becomes more positively charged. I said you should know this by now. Oxidizing agent. So an oxidizing agent oxidizes something else. So the actual definition of it is an oxidizing agent is a substance, and you may need to know the definition of an oxidizing agent for your exam because they do sometimes ask it. I've seen it in past papers. So an oxidizing agent is something that oxidizes other compounds by in itself becoming reduced. So it takes electrons from another compound, or so it oxidizes another compound, and this means that in itself it gains electrons. And so an oxidizing agent in itself is reduced. So if I was to create first of all, we need to understand what it is first. Is people get confused. They think the oxidizing agent is the one that's getting oxidized. No, it's an agent that's able to oxidize other compounds, and in itself, it becomes reduced. So an oxidizing agent is being reduced because it oxidizes other compounds. So if you want to get definition down, I haven't wrote everything down, but you can kind of get the idea from here. An oxidizing agent is a substance that oxidizes other compounds in order for itself to be, let me rephrase that again, An oxidizing agent is a substance that oxidizes other compounds and in itself is reduced. Or in case they want you to mention the word electrons, an oxidizing agent is a compound that takes electrons from another compound and in itself becomes reduced. So a reducing agent. The reducing agent is just literally vice versa of what I said. A reducing agent reduces other compounds, and in itself it gives electrons to other. So it gives electrons to other compounds. That's hence why it reduces something else. It reduces another compound, and in itself it becomes oxidized because it's reducing another compound. So reducing agent in itself becomes oxidized. So a reducing agent is an agent that reduces other compounds and in itself becomes oxidized. Or if they really want you to say the word electron, a reducing agent is a compound, or it's a substance. You can just say substance. A reducing agent is a substance that donates electrons to another compound and in itself becomes oxidized. So for example, right, so let's say we have this reaction here, right? A plus B goes to form A plus B minus. And this is probably the best example, but to show you what I mean here. So A plus B goes to form, I don't like the way it's written there, A plus B minus. I know I have the answer here, but try and understand what's going on here, right? What's going from A to, forget what's written here. I know the answer is written here, but try and understand what's going on from here to here, right? A is becoming more positively charged, it's losing an electron, whilst B, in the same reaction, is gaining an electron. So which one of the two would be the oxidizing agent, and which one would be the reducing agent? Well, B in itself, we can see B here is being oxidized because it's gaining an electron. So if it's gaining an electron, and it's gaining an electron from an A, so it's oxidizing A in order to become reduced. That's an oxidizing agent. So it takes an electron from, so B is an oxidizing agent because it takes an electron from A, meaning A is oxidized, and B in itself becomes reduced, and vice versa. A must be the reducing agent because it's helping to reduce B, whilst in itself is becoming oxidized to form A plus. And in a redox, if you have full reaction, this wouldn't be the half equation. This is the full equation. I'll get into half equations next, but in a full equation, in this sense, you would have an oxidizing agent and a reducing agent if you're making a full equation. Switch, no, fuck me up. Yeah, actually that is. Why did I do that? Alright, so just to sum all of this up now. So if we're summing everything that we've learned so far, redox reactions, we have oxidizing agents and reducing agents. So oxidizing agents, I just always like to do these little segments here, even though you guys know it from Seneca, but they're quite good because they just sum up everything that's kind of been brought up, so that you can't make sure that there's no way you can't get confused. And I always sometimes overstate things, but that's just to make sure that you guys fully know what's going on and you can't get confused. It's said 6 million times before I stop talking. Sorry, an oxidizing agent in itself is reduced. I say it's itself reduced, and because it gains an electron. We already know what you already know what reduced means, so I don't really see a point in saying gains an electron, to be honest. But is in itself reduced and oxidizing other compounds. So the important part that you need to know for oxidizing agents is that it's not the one that's being oxidized, it's the agent that's oxidizing another compound. Think of agent, when you think about agent, right? And also I haven't got the scientific term for agent, but think about a formal agent, like a footballer's agent or a sports person's agent. They're not the one that's receiving the compensation, unless you're some football managers. But on a serious note though, when you think of agent, it's not the one that's doing it. It's the one that's assisting it. It's helping a player to get the backing or financial backing, right? So it's not the one that's receiving the money or not the one gaining money. It just helps one to acquire one. So that's when you think about oxidizing agent, it's not the one that's being oxidized, it's the one that's oxidizing another compound. Right, I've said that enough times now, and it's literally vice versa for reducing agent. So is itself oxidized. And then reduces, sorry, my handwriting is kind of poor, reduces another compound. Or substance, I should say. Alright, so oxidation states and redox. Oxidation states are crucial tools for understanding redox reactions. So if we're going to get into oxidation states, right? So an oxidation state shows how many electrons an atom has gained or lost. The concept of oxidation state is related to electronegativity. Electronegativities can be used to work out oxidation states. And there are several rules to assigning oxidation states. So it's quite important. In chemistry, you might get example. Have you ever noticed when you're writing something down, right, or writing a compound down, it'll say Fe3, or have it in Roman numerals next. So it's particularly obvious in transition metals, right? or like vanadium 5 or vanadium IV if you read it in normal numerals there, right? But or Fe3 or Fe2 instead of written in normal. Though that's related to the oxidation state, and it's really useful because it's useful for telling us how a compound will be oxidized or how it will react in a way. So that's why it's commonly used, but they're very easy to work out. I remember in GCSE it was kind of difficult to work out, but it's very easy to work out. So there are several rules to assigning oxidation states, right? And rules are to assign oxidation states in a compound with multiple elements. We pretend that every bond is ionic, even though we know they're definitely not. But we ask the question, which element is going to take an electron pair? And the answer is always the most electronegative one. And this gives us our first rule. So the reason you don't actually need to fully understand this, but what it's trying to say here is we treat air like an ionic molecule because we treat it like it would be with for example NaCl, right? Na is always +1 and Cl minus is always -1. Now if we did the same example, for example, that's not an ionic compound, right? I haven't got an example off the top of my head, but like an ICl, right? Iodide chloride, right? Or they probably have a better example, but ILCl4 probably, but you can clearly tell that's not an ionic compound. It's clearly a covalent compound. But when we're working out the oxidation states, we have the same mindset of ionic compound. You treat it like it's ionic. So yeah, that's so in that case, the iode would be -7, and then the chloride would be -1. But I'll go for an example of how to work out the oxidation states because it's maybe confusing you, but it's you to kind of write it like an equation a little bit to help you find out a value. Because if you're trying to find out a value of an oxidation number, right, you write that. If you're trying to find out, you call it X, for example, and then if you have a known one like an oxygen or fluorine, for example, and you know it's the overall oxidation state of the whole compound is 0, you can very easily work out the value for X. I know this is probably very, very confusing right now. I'll just go for an example so you can actually understand what I'm trying to say and hopefully you see that, right? But for right now, there are examples of oxidation states that are always known. So fluorine's oxidation state is always -1 because fluorine, if you've seen from my previous videos, fluorine is the most electronegative compound, so it's always -1. For oxygen, the oxidation state of oxygen is always -2. I say always -2, it's actually generally -2, unless you have a compound of oxygen and fluorine, because the fluorine rule always takes priority, because that's why I was talking about the electronegativity, because fluorine is the most electronegative compound. It's always -1, it's never an exception. Oxygen is always -2, but in cases with fluorine, it's always gonna, because fluorine will take the priority in that case. But you'll see some of these as kind of exceptions to the rules, like, and I'll go on to the next one as well. But generally, oxygen is -2, fluorine is always -1. Another example is a peroxide, where I believe it's -1, in case I'm wrong on that one as well. But there are some examples, but generally to understand it, oxygen's oxidation number generally is -2. And sometimes it's not difficult to work out what it is, even if it's an exception. Hydrogen's oxidation number is always +1, except in metal hydrides where it's -1. And even then, it's pretty easy to work out that. I'll probably come back to this one to show you what I mean. The rest, so in a compound, so if a compound is an ion, the overall oxidation state is equal to the charge of the ion. So for example, if I had, I don't know, an example of a negative. I haven't got a negative charged ion in my head, like Cn minus, right? A cyanide ion, right, is Cn minus. The oxidation number is the same as the charge. So the oxidation number of a cyanide ion would be -1. In a simple ion, the oxidation state is just the charge on the ion. So a simple ion like a nitrogen ion, for example, N minus, that would just be -1. So because in an ion, the oxidation state is always whatever it is. Or if that's an N plus, it'll be +1. And then for an ion, for example, Cn minus, a compound ion, a molecular ion, whatever, in general, when you have an ion, it's always the oxidation state is always the the charge on the of the ion. So it's either -1 or +1, whatever the charge is. So in this case, Cn minus -1. In a pure metal, the oxidation state is 0. So this includes atoms like helium, but also molecules like H2. So diatomic molecules, or elements, pure elements, right, have the oxidation state of 0. Don't ask me why, because to be honest, I've kind of forgotten. I remember my teacher kind of explained to me, but I've forgotten it now. But the oxidation states are commonly represented by, as I said before, Roman numerals. So, for example, for Fe3, the reason why it's written like this is that the Fe in Fe3 has an oxidation state of +3, and the sulfate has an oxidation state of, actually, I'll probably, that is not stated here. It's not stated here, but you know the iron, which is the most important part of this compound, because this is more of a spectator ion really. If you dissolve this compound, right, in an aqueous solution, you get Fe3 plus and SO4 minus, right. The Fe3 plus, which is the priority ion, that has an oxidation state of +3, and that's why it's represented by Roman numerals. So yeah, ionic half equation. So, and that's what it looks like here, this compound here. I just say it was kind of difficult to represent it like that, but ionic half equations, right? So you already be familiar with balanced equations, but when the reaction is a redox reaction, we can make some further adjustments. So an ionic half equation shows either reduction or oxidation. So an example is, you should remember this from GCSE, but the half equation regarding O2, right? And if you remember, if you did triple science, then this is probably easy for you to remember a fuel cell. But O2, actually, I've got it down here actually. So, but this is the ionic half equation of the reduction of O2 to 2O2 minus. Yeah, the half equation. So, and if you have ionic half equations for both a reduction process and an oxidation process, you can add the two to generate a full balanced equation. So, if you had, for example, so yeah, this is the one you usually. This is an example of a half equation. I mean, it could have another example, but fun fact about this, it's kind of off topic. It's more if you do AQA biology or AS or A level biology. I'm going to be doing the biology section of this kind of these type of topics after I finish chemistry. If people really want that, but yeah, if fun topics, it's not related to chemistry at all. But this is, if you do biology and you realize this is what's actually happening in oxidative phosphorylation in cytochrome C oxidase. The reason why it's used for photophosphorylation to attract those H pluses that are next to the ATP synthase protein. You have loads of these O2 minus ions that go around the ATP synthase on the other side, of course, and they bond with loads of those H pluses, right? And then when that happens, it forms water. The water then leaves, right? And that's what allows it to, because it's forming that water, there's no H pluses there, and it allows it to be forming an electrochemical gradient. Anyway, that's completely random. You don't need to know that. I just saw that and I thought it was kind of interesting. I just remember that for some reason. But anyway, if you do remember this, now bringing it back to chemistry, and I said here, if you have an ionic equation for both reduction process and an oxidation process, you can add the two to generate a full balanced equation. Where's an example that you may need to use? Well, there's an example in year 2 that you actually do need to know this, and that's for electrode potentials. But an even easier example of that you may know, you still have to do that, is this topic in year 2 as well, but it's you first heard of it in GCSE, or at least triple science GCSE, and that was related to half cells, right? So if I was doing half cells, right, I had, I believe, H2 going to form.
Here's what I found.
Oh, Siri wants to. Sorry about that. 2E minus forming 2H plus, right? And he had if I had 2H2, right, 4H plus, that's what it was. Anyway, actually, no, I'll represent it as 2H, but I'll represent it as H2, and then you can see where I can go from here. So it's O2 plus H plus. Usually it's a 4H plus. You need 4H pluses to form 2 molecules of water. Oh. I mean, that was useful, but it's just way too late now. I'll just leave it as that, right? 4H plus 4E minus goes to form 2H2O. Now, if I had this as it is, right, I've got now 2 half equations, and I know that it's gonna, sorry, that should be 2H plus here, sorry, that's my bad. H2 plus 2E minus goes to form 2H plus, and O2 plus 4H plus 4E minus goes to form 2H2O. This is your, how many mistake here? I feel like I have made a mistake here. No, I remember that. The problem is this here. H2, 2H plus 2E minus. Right, so it has to have, remember you have to have electrons on either side of your equation, right? And the H2 is getting oxidized, and the oxygen is being reduced. I remember my mistake now. This is the 2 half equations. H2 plus goes to form 2H plus 2E minus, and O2 plus 4H plus 4E minus goes to form 2H2O. How are we gonna use these 2 equations to make one full equation? So first of all, we have to balance this first. We always balance the electrons. First of all, we make sure that our actual equation is balanced. I know there's a set of rules, so if I trigger any chemistry teachers for making it for not following the exact set of rules, but when I'm looking at this free form, I can see the 2 equations are balanced. I then look at the electrons. The electrons need to be balanced. How can I get from 2 electrons to 4 electrons? Because that's a simple way of getting from to the same number of electrons, right? I times this whole thing by 2. So 2H2 plus 2H2 goes to form 4H plus 4E minus. Now I know that both sides have the same number of electrons. Does anything cancel out? I don't believe anything really cancels out apart from the H pluses. The H pluses would cancel out. Yes, so these 2 would cancel out. The 4E minus and the 4H plus would cancel out. I'd get 2H2. So I haven't done this in a long time. So anyone who's actually seriously watching this videos, I haven't done this in a long time. So if I was to put these 2 equations together, I have 2H2 plus O2, and then you'd form 4H plus on either side of the equation. Those would cancel out. And then I would form H2O, or 2H2O. And now I've formed a full equation. From, obviously you do it much faster than that in the real thing, but that's how you would in the real thing you do it much faster than that. But if you, that's just me breaking it down, because I remember when I first did this I was kind of confused. But that's all it is. That's simply and that's all it is. I know I kind of made a mess out of it around it, but we'll move on, right? I'll probably do another video where I actually do a better example. But an example, right, is TiCl4, right? And I've got better examples here. The ionic half equation for the oxidation of Ti to Ti4 plus is Ti goes to form, is obviously different, Ti4 plus 4E minus. The ionic half equation for the reduction of Cl2 to 2Cl minus is Cl2 plus 2E minus goes to form 2Cl minus. Notice that the electrons, if it's a, you can clearly obviously see that it's that the side that the electrons are on tells you whether or not it's a reduction or oxidation reaction. So if the reduction, if it's the electrons are on the left hand side, like in the second ionic half equation, it is a reduction, because it's, remember what the equation is reduction is gain of electrons. Here is gaining electrons. And if it's an oxidation reaction, this first half equation is the oxidation reaction. Well, I know it says it here, but you can, if you, sometimes it may not tell you it, and they just give it to you here, and you can clearly see here the electrons are on the right hand side of the equation in the products. The electrons are being formed, or they're being released in this case, but they're in the product side, and that just definitely means that it's an oxidation half equation because electrons are seen in the products. But yeah, so if you want to form a full overall equation, remember in the example here, I remember I left it here, and this would be, what was it again? It would have been the same thing, 4H plus 4 electrons. If you're doing your equation, if you're trying to do your form an overall equation like this, and you have and you have electrons on the same side. I know it sounds like I'm just waffling, but it's important to understand that if your electrons are on the same side, you've either made a massive mistake, or that compound, those ionic half equations won't go together to make your full overall equation. They're both the same equation, oxidation or same reduction reaction, and it all won't form an overall reaction. So it's important to understand that there are some examples where when you do electron potentials, they'll all be on the same side, and you have to know which one is going from products to reactants, and which one is going from reactants to products. But in this case, it's very easy to see the electrons are on one side for one type of reaction, and on one side for the other type of reaction. So you have to be on opposite sides in order to cancel out. You have to cancel out to form your overall equation. So yeah, so the ionic half equation for the action for this reaction, said it here. Ti forms Ti4 plus 4E minus, and CO2 plus 2E minus goes from 2Cl minus. When adding two equations together, you must balance the number of electrons on either side so that they cancel out. So 2Cl2 plus 4E minus goes to form 4Cl minus. So basically, we're doubling. We want to get the same number of electrons we want to make sure that both equations have the same number of electrons. Like the same way how you would in maths when you're kind of, I forgot what it's called again, when you I haven't done, I clearly haven't been in school for a long time, but when you have two equations on top of one another and you're cancelling them out, you make sure that they have the same number, or the same at least one of them is the same, right? You want to make sure that one of them is the same, or both of them is the same. So in this case, the electrons have to be the same for both reactions. So the only way to do that is by timesing this by 2. There are some examples where you have to times both of them until you get at least a common factor of electrons, or the same number of electrons in this case. So in this case, you times this one. It's easier to times this by 2 to get 2Cl2 plus 4E minus plus goes to form 4Cl minus. And then when you put the two of these together, you get the full ionic equation Ti plus the 2Cl2, the electrons would cancel each other out, right? And then you'd have form Ti4 plus 4Cl minus. And I'm going to bring this back because don't really understand that. All right, so now I'm going to go through I said at the end I was going to do a part where I explain the oxidation state. So this, the half equations, you surely should know that by now. Now I'm going to be going briefly through oxidation state. So this is very simple. Some people get really scared and they don't really want to know what's going on, but it's actually really, really easy to do. Even the hardest examples, they follow this principle, right? So let's say I wanted you to find, you get a question where say, what's the oxidation state of sulfur, right? So they ask us, what is the oxidation state of specifically sulfur? We know that hydrogen is always a +1, and oxygen is always a -2. Let's call the sulfur part here X, right? So we have X. We call the sulfur. We don't know the oxidation state of sulfur. We're trying to find that out. But we know that the oxidation state of hydrogen is always +1, and there's 2 of them. So I'll write it out like this because just to show you where, instead of writing +2, but just to show you what I mean, right? And then we have oxygen is -2, so that's +4 by -2. And then what's the overall oxidation state of this entire compound? Well, it has no overall charge, so it's 0. So it would be x plus 2 minus 8, and that's equal to 0. X minus 6 is equal to 0. X is equal to +6. Remember to put plus, then you have to remember to put +6. This plus here is so important. This plus here is very, very important. Plus or minus, right? And that's it. That's literally, and now you have the oxidation state of sulfur. That's literally the way that you have to do it, right? And it's the same for iron. Like if I don't know the oxidation state of iron in FeCl2, I go X CO2 is, we know Cl is -1, and it's 2 of them. Now you know what that represents, but I'll still write it like this. You know, I'll still write it like that so people understand where I'm coming from. Equals 0. X minus 2 is equal to 0. The X is equal to +2. And it is in this case. And that's literally, and I'm going to go through one final example here. So I'm going to rub this out, but if you just get that part out. This final example, FeCl4 minus, right? Be careful with this one. It does have an overall charge of -1. So we say, if you want to work at the oxidation state of iron in this case, X, they won't give you an oxidation state of a compound you won't know anything about. Especially with transition metals, they won't do that because you're learning here too, one of the features of transition metals they have multiple oxidation states, unless they tell you specifically what the oxidation state is. So they'll probably ask you to find out what the oxidation state of the transition metal is. So in this case, if we want to work out the oxidation state of Fe or iron in FeCl4 minus, we have X plus, again I'm going to write it like this for the sake of people trying to understand what's going on, 4 by -1. The overall oxidation state of this iron is ion, not IRON, ION, because this is an iron, is -1 because it has a negative charge or it has a charge of -1. Therefore, it's X minus 4 is equal to -1. X would be +4 of that, -1 plus 4, and that's +3. So the oxidation state of this case is +3. And that's it. I know people try to overcomplicate it. It's really easy to work out. And yeah, hopefully this video was helpful.